there was the website went down today. Something is not like any of the stuff that we saw before. And so today, or I guess yesterday, maybe today, guys, I'm losing track. We saw a confirmation, including a paper, that while not room temperature conductivity, but that LK99, as it was like written in the preprint papers, is a superconductor. Not room temperature, so we don't have a confirmation of a room temperature, but we know that it's a superconductor, and I think it's also a Chinese university. And Eli, have you seen these results? And can you talk about the 100 Kelvin compared to Type 2 superconductor? If Eli is
Yeah,
available.
yeah, sorry about that.
Yeah.
So yeah, I did see the graph, right, and it looks real, and I saw actually Iris talking about it, and she said exactly what I've been thinking, going back even to the discussion of grains in the first preprint, that percolation could be going on. Percolation is where if you think about like dumping a bunch of pine needles down in the paths that would form as they cross each other is like a really maybe oversimplified description of percolation. But that explaining like some of the features of the graphs there. And it would also, yeah, so if you think about those pine needles lying down, how far apart they are and how many of them actually get close enough where you could think of an electrical contact. If that's really variable between samples, that would go a long way towards explaining what's going on in terms of difficulty to replicate.
And the one thing I wanted to talk about here on the panel is the 100 Kelvin. So replication aside, by the way, folks, if you want to see the scientist, I think his name is Sun Ye or Sun Yu. There's now a pin tweet on top with a translation of his live stream. I believe this was from 10 hours ago. So today there was a live stream on Bilibili. I translated, put it up. Andrew. Sorry, the other Andrew that we have, Andrew Coe. Undercott is his username. Sorry, I'm dealing with a lot of names at the moment. So he also posts this and talks about this. So the folks in it's not Houston, it's Department of Physics at Southeast University. They also released a paper with graphs, but they also released like a live stream where they confirm essentially that like what they see is superconductivity at low temperatures, not room temperature, 100 degrees Kelvin. However, and I think Andrew talked about this, Eli, maybe as well. You have something. The Type 2 superconductors. This is at the upper range of Type 2 superconductors that we currently have. Is that a fair assessment to folks on the call? The confirmation that they have.
Yeah. No, and I mean, if you think about it, if this had been discovered instead in 1980, I mean that would have been really noteworthy.
And specifically because other superconductors are also rare earth materials and really hard to come by, and the process is I actually don't know about the process, but this is lead and copper and some other stuff. This is like we currently have a confirmation from like a respected, I don't know if there's folks in the audience who talked against the recent kind of Southeast release. However, and I think I saw some people talking about the percolation and some other stuff. But currently today we have a confirmation that LK99 is at least a superconductor that's at least as good as current superconductors that we have. However, the process is way simpler and the materials are way cheaper and like way more abundant. Right? So, okay, if we stop today and stop like confirming everything and everything else goes to bust, but if this specific thing replicates, this is great news. And I think in perfect timing, I think while he comes up, and his microphone and connection is connecting, we've been trying to get Robert Belgrave on stage, and I think we can hear you, Robert. Hey, Robert.
Hi, can you hear me?
I think you need to press a mute. Yes, we can hear you.
Oh, amazing. So sorry, guys. I didn't realize.
Thank you so much for
No problem, no problem. I didn't realize that this whole speaking thing didn't work on a laptop. So I've been watching on my laptop and wondering
Yeah,
why can't I speak? But I worked it out. Thanks.
I'm sorry about
Thanks, Ada.
that. For first time folks, I would love for you to introduce yourself, and then if we can have a brief conversation about like generally the stuff and then the recent events. Feel free to.
Sure. So hi everyone. Good to be here. Thanks for the invite. So my name is Robert Palgrave. I'm from University College London. I kind of trained as a chemist, but I'm really a materials chemist, or you could say material scientist. So I work a lot with solid state materials, solid state synthesis, thin film deposition. Actually, you were mentioning that a little bit earlier. I probably spent the first 10 years of my scientific career doing different kinds of thin film deposition. And yeah, I'm as fascinated as you guys are by this development. I mean, I'm not an expert in superconductivity. I've never studied superconductivity before, but my angle was really just looking at the synthesis, the way they did this reaction, the kind of chemistry of it, and having a look around there, especially their characterization side. They've made this material with perhaps amazing properties, but I think, as Andrew was saying earlier, they don't really know what it is, and I think we still don't really know what it is, which for me is kind of the interesting part, because that's the kind of stuff I work on.
So I have a question for you, Robert. There was this kind of, I think part of the patent was a chemical vapor deposition. There was an addition to the patent on chemical vapor deposition. Can you speak a little bit about, like, CVD? Why did the team kind of divert into looking at CVD so quickly? What are the uses of CVD or thin film? Like, what would they end up using CVD deposited superconductivity for?
I just want to clarify real fast. The patent is dealing with a physical vapor deposition. It's a thermal deposition process.
Yeah, I think that was right. I
didn't look at it.
I was going to think maybe I missed that. So chemical vapor deposition is definitely a thing, and it's a very versatile technique. But I think you're right. Yeah, what I saw in the patent, at least, and in fact in the paper, in the first preprint, they talked about physical vapor deposition. So I mean, there's lots of kinds of physical vapor deposition. The simplest one is you just kind of heat something up, and it evaporates, and then it condenses on your substrate, the thing you want to make the film on. And if you get the conditions right, then you can grow a lot of different materials that way. Normally, you would have to do it in a vacuum, in kind of perhaps even a true high vacuum or even ultra high vacuum environment, in order to stop the thing that you're evaporating reacting with the atmosphere that it's passing through. But yeah, it's a pretty versatile technique. With thermal evaporation, you can deposit quite a wide range of materials, so it makes sense to try that. You simply get your material that you made out of the furnace, in the way that I guess they described, and put it on, put it into your vacuum chamber and then heat it up, and you get a thin film, perhaps. Now, there's a lot of questions there. So, is the thin film the same thing that you put in at the bottom of the deposition chamber? In many cases, it won't be. There's lots of opportunities for chemical reactions to happen because you're providing a lot of heat and you're putting it in a high vacuum environment. So things can evaporate, things can change chemically, and you definitely need to do a lot of characterization on that thin film to see if it's the same thing as you put in at the bottom. And it's not by any means guaranteed that it will be. So as far as I've seen, everywhere I've looked, I haven't seen a single bit of characterization on any thin film. So that's definitely something that's needs to be filled in. Second, just
okay, so they did do their resistivity measurements on the thermally deposited thin films in the first paper.
Yeah. No, you're exactly right. Apologies, I wasn't very clear. I meant chemical or structural characterization. So something to say that the thin film that they made is the same as LK99, the material that they got out of the furnace. Yeah, sure. They actually did the resistivity. You're exactly right, I think. But in terms of structural characterization, I mean, it could be something completely different. We really need to find that out. So, that's I think a big task, ahead of anyone who wants to do that. And also just getting that deposition to work. I think there were very few details of how they did it, maybe no details at all of the conditions. So the pressure, the temperature, was the substrate heated or not? How far away was the substrate from the source of the material? All of these things are going to be, something that you would need to fine tune a lot to get a decent thin film.
Yeah, in my reading of the patent, I was just going through my mental checklist of, what would I need to know to replicate this? And there's a lot of missing variables. The substrate is simply referred to as glass.
Yeah.
There's more definition. Temperatures listed from 900 to 2000 Celsius. And perhaps we could throw it up on the Jumbotron, but there's a figure in the patent, figure 6, that shows actually a gradient that's being deposited from white, light gray, dark gray to black. It appears as though it's being plating out gradually, and they don't say where the SEM figures are actually sampled from, and where the XRD is coming from. There's obviously differing compositions. It's not homogeneous in the least, and so who knows what the compositions are of all of these different regions.
Yeah, 100%. I mean, I think in general that. Sorry, go ahead. Was there more you wanted to say?
Well, I just wanted to emphasize.
You're breaking up a little bit for me. I'm not sure if for other speakers as well, but
okay, let me get on
Wi-Fi
and I'll
yeah. Get on Wi-Fi. I will say, Andrew, can you take a look and see if I posted the right thing, the patent on the Jumbotron? Andrew, maybe I'm having connecting issues.
No, I hear you fine.
Oh, there you are.
That's it. That's the right one.
Awesome.
So I just wanted to mention on the LinkedIn slide, he talks about, quote, chromatographing it into a film and analyzing portions of the film. So we know there's a variation.
Okay. Yeah, I mean, I think in general for this whole, the whole field, there's a lot of work to be done on characterization of these things. So, and I think this really goes to what you guys were speaking about a little bit earlier with all the DFT work that's been coming out. That DFT work really, so Sinead Griffith's papers and all the other papers really relies on a pretty accurate model of what this material is, because that's what they have to input into their calculations. So if you're getting the wrong material, if you're putting in the wrong material, you're going to be spending a lot of computational resources calculating something which is not actually the material of interest. So I still think there's very fundamental questions unanswered. Is the copper actually doping into the lead apatite in the way that they say it is? I don't see any evidence, any experimental evidence to say that it is. It seems very speculative. Is the copper even doping into the lead apatite at all? I think that's still a little bit open. I'm still not completely convinced that it actually does. What is the rest of the sample? So in the patent, they do actually do a little bit of quantitative analysis of the XRD, which is the only one I've actually seen. And there they show that about 50% of the sample, slightly over 50% of the sample, is actually not the lead apatite phase. So it's not 50% is other stuff. And they talk a little bit about what the other stuff is, but I think one of their labels is copper and other copper-containing phases. So not particularly specific.
And we don't know for certain that there's only one copper-doped lead apatite phase, right?
Yeah, I mean, it does. I mean, the XRDs, some of the XRDs do look like, reasonably, the peaks look like there's probably only one apatite phase there. I mean, you might expect if there were, for example, a few different copper doping of the apatite, they might have slightly different lattice parameters that would cause the peaks to shift a little bit, and that would just make the peaks kind of double up or look a little bit asymmetric maybe. And I didn't really see that, but I'm just kind of eyeballing this stuff. I think some of the stuff some of the points myself and others have been trying to make on Twitter is really just kind of eyeballing XRD patterns is not the best. You kind of have to, there's ways to do the analysis, and those ways have been known for 40, 50 years, let's say. So just kind of staring and thinking, oh, that looks a little bit like this pattern. We can do a lot better as a scientific community, and I think that's probably certainly the next step that I'd be interested in. Who can make a good sample list and actually have the skills in XRD analysis in order to work out convincingly what this stuff is.
We work with titanium dioxide photocatalysts primarily, but our team, we're dedicated to developing what we call essentially AGPI, if you will. So we're really interested in building this ability to model and predict different physics domains and different results and so on. We start with quantum chemistry. Our team is about 10 people, full-time equivalents, 20 plus contractors. We have ex-Sandia Labs, Oak Ridge National Labs people, focusing on condensed matter physics and superconducting physics and so on. What we've been doing is really sort of thinking and taking a step back and figuring out how do we actually improve the existing computational matter modeling of the system, given the sort of problems that you pointed out, Robert, right? So like we're also, not too impressed with like the characterization that's been done so far, because essentially there's a lot of hand waving, I believe, that's going on in trying to guess at the crystal structure. I remember the original paper with Sunny Griffin, that she posted a few days ago. The biggest problem that we saw there was that it assumes an ordered structure, and there's nothing based on the existing synthesis process that was reported for us to believe that this is an ordered system in the first place. So one of the first things that we're doing is trying to enumerate over a larger configuration space of like what other sort of configurations can we have with the copper doped in the lead apatite system. What would that crystal structure look like, and what would its values be? So we're currently looking at like all the standard measurements like local density of states, charge density, and so on and so forth, just to throw it in there. But yeah, certainly it's frustrating, the lack of characterization on this.
I mean, I think something that, as far as I know, that sounds like a great way forwards. Something that I don't think I've seen in any of the DFT papers, I think there's maybe 4 DFT papers out now, is actually an assessment of the stability of copper in lead apatite just compared to lead apatite on its own. So they all look at, or at least some of them look at, the stability of copper on different lead sites within the apatite, but they're all assuming the copper is there. They're only comparing, copper dope things with copper dope things, saying, oh, this one's more stable. But what I think would actually be really useful from DFT, and it could probably do it now, is to see, is it energetically feasible for copper to even go into this stuff in the first place, to even go into the replace lead in the apatite system? Because if they calculate that it's actually massively unstable for it to be there, that's probably a good indication that it's not going where, the original guys say it's going.
Completely.
One second, Deep.
Oh yeah, go for Alex.
1 second, Deep. I just want to make sure the audience kind of tracks a little bit as I'm trying to. You guys are amazing, and I'm so happy that this is actually happening. Robert, DFT is the simulation part, right? It's not like, hey, let's replicate the material in the lab and actually see it under a microscope. DFT is like, we put a computer, we give the parameters.
Yeah, Alex, if you're talking,
see.
we can't hear you.
I think somebody
I think
tell
you
you
should
like,
rejoin, Ellie. Yeah, we can hear Alex.
Yeah,
I could. I could yeah.
So
yeah,
you're talking about.
Yeah, DFT is density functional theory. That's the same theory you guys were talking about a little bit earlier in the space, if people were there then. That's what Sinead Griffiths and a few other, I think there's 3 of these papers now. It's a computational method that uses very high performance computers. It's basically quantum mechanics in a box. So you put your atoms in a box and you apply quantum mechanical equations with a lot of simplifications, and it spits out a whole load of properties. It calculates what the most stable arrangement is. It calculates the electronic structure, how the electrons are arranged in the material, and it can tell you a whole load of useful properties. So yeah, it's not an experiment. I think someone referred to it as playing video games earlier on, and as experimental chemists, I kind of laughed, because that's what I say to my theory colleagues. But it is actually an incredibly powerful technique, and it's much more powerful than it was even 10 years ago. So yeah, it's a kind of vital tool for material science.
Couldn't agree more, Robert. In fact, if you're interested, and so we're live tweeting our current, DFT simulations. We're using VOSP to figure out exactly what you're talking about. We're interested in, are there even thermodynamically favorable configurations of copper doped lead apatite? So we're comparing it with normal, non-copper doped lead apatite versus the change in the formation energy and so on and so forth with copper doped lead apatite. I just posted it in the billboard here, I guess. Like I just replied to Alex's original thing, and just wanted to add some more context for anyone who might not know where DFT comes from, right? So, it originated initially in the 50s, and the initial thinking happened in the 50s. Some of the papers came out in the 60s. The idea was to essentially find an approximation to the many-body Schrödinger equation, because just past around 1935. Paul Dirac, determined that if you could actually find the exact wave function for any solution of the many-body Schrödinger equation, representing whatever crystal structure material you're interested in, you could derive many of the sort of material properties that you're interested in. But of course, calculating the exact wave function, the solution for many-body Schrödinger equations for systems that are even remotely physically relevant is computationally intractable. And so that's where this DFT sort of comes in. I agree.
So a question on the simulation, Deep and Robert,
Please.
if you guys don't mind, kind of to bring it back to popular sci level, if you will. The simulations that are happening now may be potentially quicker to maybe see some of the effects. However, obviously replication is happening, experiment happening. We'll see a result fairly quick, right? Like Andrew's about to pop his kiln open. There's multiple labs that are already kind of confirmed, and like we're waiting for some visual effects or the visual confirmation, but also like actual like huge labs with papers that like replicate and say that what we have, let's hope that it is a room temperature conductor. Is DFT then helpful to then start optimizing this like crazy to bring this to production, to actually put it in applications? Like, what is DFT used besides what you're using it right now for, and what do you see these simulations used for this specific material or this specific process going forward?
Yeah, I love that question, Alex. The way that we're thinking about it is that we're closely monitoring replication attempts, particularly any characterizations of the crystal structure that sheds more light on it, so that we can make the DFT calculations more accurate. At GenMat, we work on something called the inverse design problem, which is that given a set of target material properties, let's say band gap and formation energy, just to pick two. Let's say you're interested in working backwards and figuring out what combination of chemical compositions and crystal structures would give you these properties. That's where I think some of these efforts, especially truly using generative models combined with DFT, will be really helpful. So let's say we have successful replications across the board, and we find out that, okay, this process is very finicky, slightly impure. What we could do is look at is, are there better substitutions, better dopants? Is there something even better than the lead apatite system? Again, assuming that we can properly model it completely.
Awesome. And Robert, I would love your take on this as well. You are, where do you see DFT is going? You said it's like way better than 10 years ago, and it's not more like, it's no longer a game at this point. Talk to us about how exciting this is once we get confirmation. Hopefully we get confirmation.
Yeah, I mean, DFT is, I don't do DFT myself, but I work very closely with people who do, and it's extremely powerful. It's coming from something, I would say 10 years ago, which could kind of support experiment, to a place now where, as we just heard, where DFT can really lead experiment. So you can make a huge number of predictions using DFT, and then the experimenters can say, okay, I'm going to pick the good ones and go and make them in reality. So in this case, I mean, it's actually probably gone the other way around, in that experiment has led, because the experimental results were first. It didn't come from theory, it came from experiment. But DFT and experiment, or theory and experiment, let's say more widely, are very much of equal footing now. If you see a DFT paper that predicts something and it's from a reliable group, then it's probably right. So whether that thing can actually be made in reality, there may be some other issues. But yeah, I think DFT will have an important role there, and it might be, that once we understand why this works, because there's going to be a lot of new physics here if this is genuine, it might be that, the lead apatite doped with copper is not the optimum system. There may be many better ones. Once we understand the idea, we might be able to then go and design for to find the same structure, to find the same kind of arrangement of atoms, which will give us maybe even better properties, which maybe maybe much more useful. So I wouldn't necessarily go and put all your money in lead and copper stocks right now. There may be it might not be that comes out at the end. But sorry if you guys already have. You're probably okay for now. You're probably okay for now. But I think there's a long way to go with this. I wouldn't necessarily see this material as the one thing that's going to be commercialized. But if it's true, it's a massive breakthrough, and it's going to spur on a whole load of new research for decades to come, I would think.
So just to add to that, about 1.5 hours ago, Korean media has dropped a email interview with Hyun-Tak Kim, where he basically says, like, I believe the characterization is done, and you guys can go and check, and the other overseas crooks can check, and that he's willing to assist people who are doing the characterization, but he himself has moved on to researching new substances.
Wow.
Amazing.
Really? Wow. Okay. So breaking.
So I'm gonna drop that. I'm gonna drop that to the room here.
Yeah, add this to the Jumbotron, please. We want to follow, and thank you 8to5 for breaking news. And like, I want to ask Robert. Robert, you're looking at this. You're saying if this replicates, last space we had, and I think this was way before. I think even Iris Alexandra showed us some of the replication attempts in the living room, and then definitely before the Hoost Institute and some other folks, and I think before Sinead released the DFT paper, folks gave percentages. I'm not going to put you on the spot into the percentages, but I do want to ask you specifically, what do you need to see to get to, we have a room temperature superconductor like in our hands in this material? What else needs to be done?
Well, I mean, for me, as not a superconductor person, it's hard for me to judge, is the current, resistivity, heat capacity measurements, or do we need more? It's kind of hard for me to say anything, basically a layman's answer to that. What I'd want to see, if we do get something, is we need to throw every bit of characterization at this. I'm still pretty doubtful that the explanation they came up with in the
characterization. I'm sorry to interrupt.
Yeah, sorry. What I mean is, okay, let's use something that I maybe said in an earlier tweet. If you want to, if you design a new material that does a fantastic thing, for example, room temperature superconductor, what you want to know about that material from a chemistry, material science point of view is, what atoms is it made of? So what elements are in there? Is it lead, oxygen, phosphorus, copper, etc.? And secondly, where those atoms are in space, so how they're arranged. So the first one's called the composition, the elemental composition or chemical composition, and the second one's called the structure. So if you know those two things, then thanks to what we've already been talking about, all these theories that we have, all these computational power, we can know almost, I'm not going to say everything, but almost everything about the material. If you just understand those two things. But at the moment, we don't, as far as I'm concerned, we don't understand either of those things about this material. We don't know what elements it contains, for sure, because actually what they produce is a mixture of a whole load of different stuff, and they haven't really put much attention into understanding what elements are there. And secondly, we don't know the structure. They came up with they did some X-ray diffraction, which is like the gold standard really method for understanding structure, understanding how atoms are arranged in space. But the way they interpreted it is like, I would say not at a high level. There's a lot more stuff that they could do. They kind of looked at the pattern and said, well, it looks a little bit like this, and then that's kind of it. There's many levels of analysis you could do above that, which will give you very detailed, quantitative, numerical information about the structure, measuring the exact bond distances, measuring the exact composition, the exact arrangement of the atoms, all of these things, which would give you, that level of detail that we need. So I think in terms of composition, what elements are there, structure, how are they arranged? We don't really know the answers. So we're basically at point zero in understanding this material from a chemistry point of view. So I can't really speak about a superconductor. If it's a superconductor, it's a superconductor. That's amazing, But there's a long way to go in climbing this hill to understand what the material actually is. But that's kind of fine, because if it's a superconductor, if it really is, and people can replicate it, the superconducting properties, then every lab in the world is going to want to do this. Every lab in the world is going to want to spend time on it. So it will get done. Yeah, sure.
Could you please continue with every lab? And given the fact that we've seen replications happening in like living rooms, and the materials are way cheaper than previous superconductors, can you start us on a path, and then folks on the stage will join as well, of what this actually means? Like, many folks here for superconductors maybe for the very first time in their lives. Some of them maybe heard from us on previous spaces, MRIs, fusion reactors, all of this, like, very space tech and like forward. Could you talk at least about some stuff, and then everybody else can also chime in on, like, what does this actually mean to science? What does this actually mean to have a superconductor with these cheaper materials, with this ease of kind of baking, given that it replicates and given it's like applicable in wire form, let's say?
Sure. Well, I mean, I think you mentioned a few of the technological examples. I'm definitely not an expert in applying superconductors to real life technology, but all the examples you gave are great, and they're going to be revolutionary in lots of different technologies. From a science point of view, I think what we will learn a lot, because if this is a superconductor, it's a new kind of superconductor. Yeah, it's not the same kind of superconductivity we've seen in other materials, because it just doesn't behave the same way, and it doesn't have the same kind of structures that we've seen before. So we will definitely learn a lot of new physics from this, because we will understand, that electrons can actually behave in a way that we hadn't really considered before, in structures that we hadn't really thought about before. So I think I'll probably leave it there, because I don't want to talk too much about the technology that I don't really know too much about. But certainly for physics, there's going to be lots of knock-on effects that we probably can't even contemplate at the moment, maybe in completely different areas. Ideas from this could spring up in all sorts of different areas of physics and just revolutionize things that we don't even know, can't even think of at the moment in 10 years time. So if it's true, that's going to be one of the big impacts, I think.
That is so well said.
Go ahead.
Yeah, I was just going to add to what Robert said, especially the new physics point. I think that's super important. Other domains being impacted. The most recent example I can think of is the SYK model, the Sabir-Yekataev model. It's a statistical mechanics model that is essentially used to describe strange metals. So strange metals is a phase of matter that shows up with certain superconducting materials that happens right before you enter the superconducting phase. It's a very, very poorly understood phase of matter. SYK is fascinating because essentially the statistical model of physics that at least describes for certain, you're able to analytically calculate the ground state of this SYK model, which generally correlates in various different excited states and so on and so forth. You can sort of predict or make useful predictions of strange matter, if you will, or strange metals is the accurate term for it. Now, the mind-blowing part is that the SYK model was discovered to also essentially capture the physics of two-dimensional, aka one-dimensional black hole with one imaginary dimension black hole physics. So the sort of implication there, right, and of course this is still speculative because these kinds of black holes don't exist. Implication is that a lot of the sort of physics that are happening in condensed matter systems might actually be occurring right at the black hole level, or be useful for understanding that. So that's just an example, to add to Robert's point, where discovery of one kind of interesting phase of matter has affected how we think about astrophysics. And I can absolutely see something like that occurring here. If these superconductors are real, then it basically implies, exactly as Robert is saying, that there are unknown mechanisms, because we know, there's no way that electron-phonon coupling, for example, and Cooper pairs are occurring in this kind of material, right? So we know that has to be something else. We also know that even till today, since the discovery of the high-temperature superconductor with Bednorz and Alex Mueller back in the 80s out of IBM, since then, 40 plus years later, we still have no statistical physics model that
Hey, Dip,
actually.
just sorry to interrupt. I want to say thanks to Robert because he needs to go. Sorry to interrupt, man. I
Oh
don't
yeah,
like
no worries.
interruptions. Robert,
Yeah, thanks so
I
much,
just wanted to
Robert.
tell you thanks. And if you want to add some stuff before you leave, feel free. But folks, definitely give Robert a follow. Robert, will we see more of like more from you? And yeah, feel free to like
Yeah.
plug in whatever you.
Thanks so much for the invite. Yeah, we may or may not have some ovens running at the moment with some stuff in, but you'll hear in due course, hopefully.
Let's go. Good to Robert.
All right.
Thank you
Let's
so
go.
much.
Thanks a
Thanks
lot.
for joining us.
We'll
Hell yeah.
I think Robert, I added you to the group chat, so feel free to we have Andrew there, we have Iris there. Feel free to like run ideas by there, and then definitely do this open source. This is what we're here for, and I appreciate you for coming. So
Thanks a lot.
I do want to and Deep, I'll get back to you in a second because Robert did tell me, like, hey, the stuff that you covered are great, and we did talk with Andrew previously about several applications, and one of them that I do want to talk about, and maybe folks on stage also, is the current stage of energy and the current stage of fusion reactors. So one of the current uses of superconductors, as we know them today, right, is the first one, the older one, is used in tokamak reactor, which is like one of the biggest ones, and then it looks like Helion Energy, the guys that some. I think Sam Altman is backing, and they are supposed to give us something. I'm sure the Helion Energy is like scrambling. Like they are not only Robert and folks on stage have kilns running. I'm sure the folks in Helion Energy also have stuff running. Helion Energy essentially moves plasma with magnets. This is kind of how they do this. It's way more than this, right? But like they have a very nice popular video if you like to understand like the I think sixth generation of fusion energy, and they essentially move plasma with magnets to then generate energy. What I heard somebody refer to, and I don't remember the exact quote, is that at some point, right now, it's the energy that they need to use to run this reactor is way bigger than what they're able to get out of it. Uh, big part of the reason potentially is the magnets that they need to have like very strong magnets, so a lot of current. So they actually need to put a lot of energy in to get energy out. But the process is clear. Like we know how to do this. They know how to do this. And at some point, like the person who reported on this said, it's boring to even see kind of the flash of energy that happens when like the two plasma rings combine and get energy. So this is current. This is what happens today. And even back then, even 8 months ago, Helion Energy said, hey, this is like the older format of our reactor. Now we're talking about the potentially like way cheaper and way easier and like and cheaper because just to like make it very clear, cheaper because the materials that go into LK99 are way cheaper than the previous superconductors, which required like rare earth materials, but also because if we're getting to a replication, which I'm getting increasingly convinced, also because the energy to kind of keep them super cool, the current type 2 superconductors, the energy that's required to keep them super cool, and I think pressure as well, is also part of the overall number. And so we're looking at a potential of increasing significantly the ability to generate energy with fusion. And somebody explained this to me, and at some point my like brain broke, the exploding head emoji, when they told me that like at some point fusion reactors can get to self-sustaining process. Self-sustaining. So the fusion reactor can generate more energy that's required to run it, but also then keep generating this energy, and all essentially you'll need is like materials and maintenance, etc. And that's insane. And so this broke it for me. I was like, fuck, okay, so we're dealing with climate change, and potentially now we're looking at a potential solution for a lot of energy generation.
Well,
And somebody was like blowing up.
Have to stress that energy has caused the way we've obtained energy has been much of how we've caused climate change. But if we had like zero emissions tomorrow, there's so much carbon dioxide in the atmosphere that would continue to drive continued heating for a long time. I won't get into the details, but some of the IPCC predictions on how fast that comes out of the atmosphere might be questionable. I'll just leave it at that. But either way, we've got the mess that we've made for centuries still in the atmosphere. And
wait, Eli, hold on. So I appreciate your comment. This was not the point I was trying to make, and so I don't want to really go to like a climate change account. There could be potential new applications there. I'm just talking about the current stuff that we have, the current literal current technology that we have that's using superconductors right now. That if this materializes, like potentially fairly quick, because quick to produce, quick to test. I don't know about application. I don't know like if it replicates, etc. But the current technology right now for generating energy that exists, it's not feasible energy-wise, and this potentially will be. I also want to say hi to Joseph. Joseph is joining us via VPN. Joseph, I hope you're still here. Thanks for holding, man. Joseph was.
I'm still here. I'm enjoying this so much.
Oh, thank you. Joseph has been on stage before, and why don't you introduce yourself briefly, and then talk to us about a different application than we couldn't even think of that you started, and then please take us forward.
Hi everyone, my name is Joe Douglas. I'm an industrial designer. I focus mostly on innovation and consumer end products. I've been a CEO of machine learning companies, but I've also been a CTO and engineering resident at manufacturing companies producing large-scale electronic art installations and motors. I currently work in electromagnetic micromobility design, specifically next-gen electric unicycles. Very weird, but my introduction to this space comes from my previous work in small-scale magnetic levitation and control systems. And around 2015, 2016, we were designing subsurface omnidirectional magnetic robots that could control things above the surface via an omnidirectional magnetic attractor that would drag essentially an object from A to B. This has applications in manufacturing, but it also has applications in more consumer spaces like factory layout, warehouse layout, home layout for the mobility impaired, etc. But what I want to talk about today is actually commercializing LK99 or a derivative of LK99, assuming it's a viable ambient pressure, room temperature superconductor. So when I think about this, the way that I think about it is that it has less to do with whether or not it's a real thing and more to do with, is it a manufacturable thing that can be produced in a high enough yield with a yield rate of a viable yield rate that is high enough to justify the manufacturing expenditure, such as retooling,
yield,
Okay, so yield in the context of manufacturing, not the context of the core physics, like the fundamental physics. I'm not talking about that. Other people are smarter than me, like Andrew, have spoken to their approach to yield from a production standpoint of producing the material. I mean manufacturable yield. Once you have an actual material, say you have the copper dope lead acetate and it works, then you have to design a research and development procedure that determines, can this be integrated into our existing system, like our electronic system, our motor system, our generator, whatever. Then you have to go through design, exploration, and validation, and then you have to go to manufacturing production design, meaning you design the method of modifying the material into a form that fits the needs of your application. And then you have to go into subcomponent manufacturing, installation, maintenance, and repair. So that loop, that has to happen for every potential commercial application of this technology if the technology is viable in the first place. And that takes a long time from design to design validation to design freeze to manufacturing to commercialization. And depending on the results that we get from the fundamental research as to whether or not this is something that actually is producible using standard like thermal deposition methods, like or thermal physical vapor deposition methods. That determines whether or not this can be produced in coils. That determines whether or not this can be used for superconducting coatings, and that determines whether or not this can be used as gates in between other electronic components. And if it is something that can be produced with thermal physical vapor deposition, then it can be integrated into another process to apply that thermal physical vapor deposition onto another component. And all of that process has to get worked out at the R&D stage at multiple points. So there's the R&D stage at the fundamental level of whether or not this is producible in the first place. And then there's the R&D phase within the commercial entity that determines, is this producible and applicable to the system that we already have up, or do we have to retool and re-engineer our manufacturing plant, or do we have to re-engineer the core product that this is being affixed onto? So in the context of like, say you're using this in aerospace and defense, you'd be applying like a superconducting coating on top of other sensors or inside of a sensor stack. And the results that you get from the lab determine whether or not that's viable in the first place. And then you have to determine how that fits into your existing manufacturing supply chain, your manufacturing process and the supply chain. Now,
so Joe, I want to say one thing. You're saying you have to, and like this is a manner of speaking in English, right? Like when you talk to the person, like you have to, as an example. However, I want to highlight this one very important point, and then let you continue. Is that once we have a type of material like this, right? Let's say all of the stuff that you said are applicable, that is like reproducible as much, etc. Capitalism turns on. Recession is fixed. Like like so much money is going to get poured into this. There's not going to be like one you doing all these things, right? This scales up significantly. There's so much that's restricted by just pure energy that just the energy transfer alone, the cheaper, is going to make so many things better. But you're thinking about like other more advanced stuff, right? So not only the energy production potentially is going to be cheaper, or transfer of energy is going to get like less lossy. There's more new stuff that happening. So what's possible that wasn't possible before, Joe? That's what I wanted you on stage for.
Okay, what's possible that wasn't possible before are superconductive coatings for turbine generators that can reduce energy loss dramatically, that can increase efficiencies by 15-20%. And the reason that I brought up all of the things that you have to do is because when it comes to implementation, you're in a battle between efficiency and cost of implementation to acquire said efficiency. So if that efficiency is marginal, 1 or 2%, then a manufacturing plant manager or a procurement officer at the US Navy may decide that this may not be worth it. But if it's in the area of 10 to 15%, then they can justify the cost of implementation. And the cost of implementation is usually 1 to 2 years of the benefits of that newfound efficiency. So it's not just about new efficiencies that are created, it's about how do those new efficiencies compare to the cost of acquiring those new efficiencies. And it's also about, as opposed to efficiency, it's about new capabilities. So new capabilities are very hard to price. And there are things that people advocate for, and that's where all that new R&D money and all of the exploratory development money really goes. It's towards acquiring those new capabilities. So if you could acquire new capabilities that improve the range of a radar sensor by 50%, it's worth it to make that investment cost. If you can reduce, if you can have a thin film superconducting component for a consumer device like that would go into your battery and increase the longevity of your battery by 20%, and make the concept of thermal runaway completely impossible, because there's no loss, there's no additional heat. So your lithium-ion battery doesn't have any thermal runaway components that are intrinsic to the battery outside of major damage. That increases the safety of an electric vehicle. And all of those things are
safety and range,
they seem
right?
like Safety and range. So like safety and range
and
are
also the
huge.
cost, because lithium ion is like way more expensive than copper and lead. I want to get to thanks, man. I want to get to Deep. Deep, you have your hand up, and before you get to the stage, I want to say this like one. In addition to what we're seeing for the past 5 days, was it 5 days or 7 days? The guys told us they worked on this for 20 years, like LK99, more than 20 years. But in addition to what we're seeing the last 5 days, for the past year, I, as a person, got like superpowers in AI, right? So just literal superpowers in preparing all of this to you and understanding some of the science that's involved in like translating Korean, like all of these things I was able to do throughout all of this, and kind of talk to people at their level just because I have like 2 friends in AI. So I don't want to turn this into AI space. That's tomorrow. You guys are welcome to join that. However, we're now meeting a potential exponential curve. I don't even know if this is exponential. That adds to existing exponential curves that we have in AI and hardware. And that hardware is technically also improved by power consumption and significantly so. I think somebody talked about logic gates. I don't remember who that was. They talked about logic gates. Just to give you guys an example, the field that Deep is going to talk in a second about that runs on like GPUs, how revolutionary this could get. Jensen from NVIDIA, the guy that is now running a $1 trillion company. Atapai, I want to say goodbye and then I'll continue. I have a long speech ahead, but Atapai, you want to
Okay,
say bye
I
to
mean,
folks?
I'll just say thanks for having me. It's been very exciting, and yeah, I'm excited. Let's see if I can squeeze out another report for tomorrow. Cheers.
I will say this for folks in the audience. Atapai, I followed you like since the start here, and you floated the idea of like maybe writing a book. Write a book that I think that this is, but in potentially, right? Like we're seeing more and more cases there. It's so big that the origin of this is going to be murky. Many people are going to do their own take. I loved your takes, folks. Follow Atapai and Atapai. Do this, man. This is going to be very interesting. Thank you. Yeah. Go ahead.
Awesome, Alex. Yeah, the computing side, I think, is going to change. Superconducting will change computing drastically, right? So, like, for example, take today's best quantum computers like Rigetti, IBM, Google Sycamore chip. These are all based on superconducting architectures. And one of the biggest problems with these superconducting architectures is the fact that you need to supercool them to millikelvins, right? Thousandths of a degree of Fahrenheit above absolute zero. And so if we can drive down the energy costs of like just, implementing these superconductors, we'll be able to maintain coherence for longer and easier sort of states. And that will improve generally just the scalability of these architectures. And what we're going to end up seeing is a singularity loop. So, what do I mean by a singularity loop? If you have quantum computers that are at scale functioning, let's say tens of thousands
Deep,
of
you
qubits.
remember I did not specifically want to turn this into AI because me and you can go all night, man. Once we get to AGI, that's the end of it. But I do want to
Yeah.
talk
So
about
then,
LK99 specifically. But
yeah,
speed, generally, we're talking about like insane 100x, another exponential curve that joins the existing ones that we currently have. And I specifically
certainly.
wanted to talk to you about the stuff that you're working on because you're doing what, material modeling?
Exactly. We do materials modeling and generative
And
design
you're
of
restricted
materials.
by GPU power, and GPU power is restricted by literal energy from the wall.
Right.
So,
Exactly. You
yeah,
got
talk to
it.
us about this.
Now, the other
So,
interesting application, though, that I don't think I've heard too many people talk about with superconductors is with LK99 is the sensor side. So there's a whole class of quantum sensors that are called, in this case, superconducting quantum interference or interferometer devices. These are magnetometers that detect magnetic fields to up anywhere from 1 million to 1 billion times greater sensitivity than magnetometers that you can purchase off the shelf. So, what would that mean, right, for humanity? One is
tell me
that
the scale again, please.
it's
And
anywhere from 1 million to 1 billion times more powerful, these superconducting
then
vapor
an
particles.
MRI, let's say, than
Yeah,
the
that
MRI that
well,
we use currently.
I mean, MRI already uses superconducting materials, but these are sensors though, right? So,
Oh, you're talking about like sensors outside of. Okay, go ahead, please.
exactly,
Sorry,
like a
confused.
handheld magnetometer, let's say, right? Like, you know how some people will go weekend hunting for treasure, right, with a magnetometer on the beach or whatever, look for, right? So that's the kind of stuff that I'm talking about will get completely revolutionized. That will change our ability to look for ferromagnetic minerals for mining exploration. It will significantly drop down the cost of mineral discovery. Were you
Mining
gonna say something else?
explorations on Earth is like one thing, and but also there's like material out there, and I don't know if Andrew's still here, and if you want to talk, but you guys are you're working on space stuff. How does this specific area that Deep mentioned? How does this like, the 1000x, let's say, ability to mine an asteroid and the additional energy to come back from it? How does this affect the space industry?
Yeah, no, it would be absolutely revolutionary to be able to utilize resources in situ in orbit, so we don't have to drag them up out of the gravity well. You know, we expend 99.5% of the fuel just to get the mass into orbit and impart that velocity. So it is it would be absolutely game changing. But my I don't spend a whole lot of time dreaming that far into the future. Unfortunately, I'm pretty pragmatic and dealing with the problems of the day. So my imagination is limited as to how far it could really take us and what we could do with that level of capability.
One point on that is, space is kind of cold, and the superconductors that have already been established can probably be really useful. It's just a matter of dissipating any heat that builds up as you're using them, which is kind of the case for a lot of things in space, like the Apollo astronauts. They part of the challenge to keep them alive was actually keeping them cool when the moon it can get pretty warm.
So, sustainable space exploration, is that what you're saying? Or is that what you're hinting at?
Yeah, I mean, so
Sustainability of like a colony, let's say somewhere, gets potentially unlocked.
I wouldn't say unlocked in that we can still have.
I'm just fucking with you. Sorry, dude. I literally am just dreaming right now, and I think at some point excitement is okay, but I think also too much excitement maybe is unwarranted at this point. And I interrupted with something that I dreamed of after you just said two words, because like it's really hard for me to contain the excitement. And I also noticed that Scandi Naval is here, and he claims that sorry, on his profile it says PhD in physics. And Andrew dropped. Oh, I want to say thanks to Andrew, folks. We've talked about Andrew before. Andrew, good luck tomorrow, and the next batches will also good luck with them. We're all gonna see the Twitch that you're gonna post, and hopefully the Excel sheet that you've talked about, folks will sign up, and maybe we'll have folks here that will like send them your way. Have a good night, Andrew. Thanks for coming. And Scandinavian, you raise your hand up, and your profile seems interesting. What do you think about all this?
Yeah, mic check.
Perfect. Yeah, go ahead.
Yeah, hi. I'm a Finn. I did my PhD actually in the early 2000s here in Finland on superconductors, mainly for sensor applications, looking at mainly low TC. So we were working at 100 millikelvins up to 10 kelvins, so low temperatures. But during that time, I kind of learned the ropes on superconducting theory, BCS theory, and all that. And I, obviously, working with superconductors, cooling these things down to 100 millikelvins was always a pain in the ass. So I've always been interested in high temperature stuff. We were also working on junctions, so these will be superconducting insulator noble metal junctions for basically quantum cooling. And I actually happen to know also the founders of IQM, which is a Finnish quantum computing company. But yeah, this stuff with LK99 has really captured my imagination. even though I have to say that, having read the original papers from arXiv and some of the more recent ones from China, some of the experimental techniques are, how would I say, rudimentary. The measurement accuracies are pretty miserable, and you could actually get much higher dynamic range in your RFT measurements, your current voltage characteristics if you just do it properly. So the data is a little bit fuzzy, I would say. The most recent paper from China, where they show this anomalous transition between 220 and 300 kelvins, is clearly a measurement artifact. You can only see one data point on the transition. That's not real. Superconductors, they do have a width in the transition, which is basically governed by laws of physics, and that width tends to get larger as you go up in temperature. It's all to do with thermal fluctuations. So seeing a transition with no data point or one data point, that's a glitch. That's not real. So I wouldn't get too excited about that. That said, so I was kind of ready to throw my hope during the weekend, but then these DFT simulations came out, and this flat band evidence, looks promising. It is, well, I mean, it doesn't necessarily mean high temperature superconductivity, but it could possibly do. So if the theory side starts sort of supporting these things, and the 110 kelvins for TC is pretty respectable, it's pretty high. It's up there with, it's a new material, it's a new high TC material. So that by itself basically justifies substantial added research on the topic. Yeah.
I think we need to, and I completely agree with you, Scanny Neville. I would just temper yours and everyone else's expectations. I know you're already super reasonable about this. I don't see enough sufficient evidence, and Robert was saying something very similar earlier, that we haven't seen yet from the theory side if copper doped lead apatite is even thermodynamically stable and favorable. So let's first find, thermodynamically favorable configurations of the copper at 10% doping, and then go from there. I think that's a big part of all of this.
Yeah, I totally agree that we are not. I don't think it's well understood where does the copper actually end up in, because the thermodynamics seems to suggest that the place we think it should be, it's not necessarily going to get there. With respect to the applications, I mean, quantum computing, yeah, maybe, but I'm not a qubit expert per se, but what I do know is that the decoherence times in qubits are quite strongly correlated with temperature. It's just that your lattice is vibrating like crazy at 300 kelvins. And one of the key problems in quantum computing is the coherence time. So that's basically the time that the quantum superposition is held within the qubit. And that gets shorter and shorter the more kind of decohering interference you get. So I wouldn't hold my breath for room temperature quantum computing at this stage. The other thing I should say is that superconductors, strictly speaking, only maintain zero resistivity at DC, so very low frequencies. So all the IT applications, the processor applications, all of those things are pending on better understanding of the AC losses of the material, which has primarily to do with the kind of the way the current gets configured in the superconductor at non-zero frequencies. I worked myself on superconducting sensors. This could potentially be quite interesting, which is that the most sensitive electromagnetic sensors we currently have or have deployed are so-called transition edge microbolometers or calorimeters. So at low temperatures, people have developed sensors that get like super high X-ray resolution for X-ray photons by basically measuring the infinitesimally small temperature rise that the X-ray photon causes when it gets absorbed in a thermally isolated absorber. And the thermometer is basically a superconductor that's maintained within the middle of its transition. You can do the same thing with power, and that's what it's called bolometers. Bolometers, the most common that you are mostly aware of are thermal infrared cameras. The uncooled ones are actually based on microbolometers, and they use just a high temperature coefficient material for the transduction. But if you had a superconductor maintain its middle of its transition, you could well get, you know, an order of magnitude improvement, or maybe even more, for thermal cameras. So that's kind of an interesting application. Anyway, that's just my 2 cents. I just wanted to pitch in, and thanks for the space. Thanks.
Thanks for coming up.
So
Specifically, the point
before you go, actually, you mentioned cooling. Could you go into that a little bit?
Yeah. So if you have a superconductor that's connected by a tunnel junction into a normal metal, basically when you apply a voltage across that sort of junction, you know, if you look at the Fermi distribution, or the energy distribution of electrons on the normal metal side, most of the electrons reside on the Fermi level. But as you apply a voltage, a DC voltage across the junction, you basically blow. So basically the hottest electrons on the normal metal side have a finite possibility of tunneling across the junction barrier to the superconductor, where they pair as Cooper pairs, or whatever bosons they form, and that heat is then basically pumped away from the normal metal. And at low temperatures, at the, you know, in the late 1990s, early 2000s, we were able to show, you know, we were able to cool the normal metal by a factor of 3, basically from 300 millikelvins to 100 millikelvins. You know, it's not a big delta T, but it's a factor of 3 in temperature. But it gets easier at low temperatures, because the thermal coupling of the electrons to the lattice is a very weak. It's a very strong function of temperature. It goes to T to the 4th, basically. So the electron gas in the normal metal gets completely decoupled from the lattice of the metal. So it's kind of thermally isolated, the electron gas. So you're basically just cooling the electron gas. But it has some applications in sensors, potentially quantum computing. It's actually, some of these things are applied in some of the qubits to bring down their effective temperature and thus increase the coherence time. And there's no reason why you couldn't do that at higher temperatures, but you would have to engineer the thermal bottlenecks, because you can't rely on the electron phonon decoupling at that stage.
Hi, mic check real quick.
Yes, I'm with you here. Go
So
ahead.
one thing I wanted to ask while we have some experts on here, Ben Schendel, who is in this group kind of following this, was talking about the fact that in the paper that a lot of people have criticized from the Southeast University, that they measured both the resistivity when they were going down in temperature, when they were cooling it, and going up, which would seem to me to answer some of the questions around whether or not it was just like a measurement issue. But obviously, this is not a professional view on this. Just wanted to get your all's take on that. Would that lend any more credence to the idea that the drop in that paper that you saw at like I think it was like 260 Kelvin, would that lend that any more credence? The idea that they checked it both down and up, or can temperature affect the way that these probes that measure resistance like interact with the material, I guess?
Yeah, in principle, that does bring some more credibility to it. But my hunch is that it's a measurement artifact. So as you go up in temperature or down, you know, there's a preamplifier in whatever voltage meter they're using, and I'm thinking that it's probably switching range there, and there's something wrong with the amplifier on a different range. You know, it's auto ranging as you're dropping in R, and that those things often generate those sort of artifacts, unless, and you know, it could be that the instrument is maybe not working properly or something like that. But I just find it really suspicious that there are no data points, because they're going down pretty slowly. I mean, if you look at the density of data points on the way down, you know, there's lots of data points there, and the transition at 110 kelvins is kind of a reasonably, that's what you would expect to see. But you know, this kind of a completely discontinuous drop down by 2 orders of magnitude, I don't
Yeah,
think
that's what I kind of wanted to get at, is that like I just wanted to know whether or not the fact that they were able to measure it while cooling and then while heating it back up measured the exact same thing, if that's explainable from a like from a sort of an equipment defect or a misuse of the equipment, I guess.
Yeah, well, I mean, you know, the amplifier is going to be auto ranging at the same voltage level, whether you're going up or down. So it would reproduce the same glitch whether you're going up or down.
Thank you. I had been just wondering about that. Appreciate it.
One, by the way, interesting application. I don't think anybody has talked about it, and it's not my idea. I read this
tell us.
somewhere.
I'm excited.
Yeah, 20 years ago. So I think we could have aircraft without engines, because you could basically introduce hydrodynamic drag on air. Think about an airplane where the leading edge has some sort of apparatus that ionizes the air. And then you coat the wings of the aircraft with a superconductor like this. So you can run crazy currents, over the surface of the airplane, the wing, which would induce hydrodynamic drag on the ionized, air molecules, just thus basically generating thrust. So I think that's a pretty cool thing.
So I just want to ask you from my dumb self. The folks are talking about hoverboards from Back to the Future. So let's say very low, and they, let's say, are based on some magnet pinning or whatever. You're talking about moving ion in the air? I just want to make it clear. No engines on planes potentially, just current?
Yeah, I mean, leading edge, you ionize the air. So you have some sort of a high, either discharge or high voltage. It doesn't necessarily need to dissipate a lot of energy, but it just ionizes the air sufficiently that when you apply a superconducting current from the leading edge to the trailing edge, that current is going to basically attract by electrostatic forces the molecules to move along with the thrust, and thus you have an engine.
That's fascinating, Scandinavian. How would you imagine hypersonic travel, where there's going to be natural ionization simply from the speeds that you're flying at, melting the air around you?
Absolutely. Then you don't need to pre-ionize at that stage, and obviously
Nice.
going fast is a lot easier if you don't have nacelles and nozzles and intakes and all these sort of horrible aerodynamic shapes in your aircraft.
Love it. I also wanted to go back to the space applications too, since you brought that up. Another interesting application, right, beyond just using superconductors for compact nuclear fusion, is you could probably coat, and love to hear your thoughts on this, Scandinavian, is like you could probably coat your craft with the superconducting material and then run a current through it and then use that to deflect charged micrometeorites and microparticles in space when you're traveling at subsea, right? Like even the smallest particles can destroy your craft. So imagine being able to deflect at least the charged particles coming at you. Do you think that's possible?
Yeah. I mean, I can't do the math in my head, but you probably do need ridiculous large magnetic fields in that case. But yeah, I mean, why not? And the other thing is, we're talking about ion engines. One of the concepts for interstellar craft is that you generate this magnetic funnel for interstellar molecules or atoms that you then kind of suck into the ion drive, so that you don't have to. You could get the propellant on the way. So this could be one space application as well.
I don't want to interrupt you guys nerding out on like space application. I just want to highlight Scandinavian. I don't know if you for doxing yourself or if you're Anon, but you have a PhD in physics, right? And when you say why not, are you basically like saying there's no like physics restriction to this, like, right? We just need whatever's in front of us coming potentially closer.
I'm just ignoring all of the engineering problems that even if this thing gets proven that it really there is a new mechanism that has the possibility to have a superconducting material at ambient temperatures and pressures. That's one thing, but obviously we shouldn't underestimate the engineering challenges. In first of all, coming up with a manufacturing method that's sort of industrial, and then these appetites are fundamentally really brittle. I guess the same applies for IBCO and some of the other high TC materials. So that we've figured that out. So we'll figure that out too. But it's not going to happen over 2 years. I think
it's a start of
It's a
start of a long road. Yeah. Long road, but forward and accelerating ever more, because we also can get AI and AGI to help us kind of design this. AGI is a whole big thing we're not going to touch in the space, but AI multiplied by 1,000 can help with many of these manufacturing things, and robots that now are able to get powered for a longer period of time can go and do them potentially, right?
Yeah, and then there is some, let's say, different fields of science which also are, becoming more and more relevant. Synthetic biology, even though you would sort of not immediately think about synthetic biology and superconductors, but some microbes, they actually output minerals. So could you genetically engineer a microbe to synthesize copper apatite? I don't know.
Well, yeah, just
could be done. I don't know.
Remember that our teeth are hydroxyapatite and fluoroapatite, so there are proteins that template that.
Exactly.
This is something that Iris brought up too, is that there would be some like microbiology applications if this were to actually be a superconductor, where there are certain like strains of bacteria, I think, that are basically that are conductive, that you could like introduce into the synthesis. Now, this is obviously a very layman's explanation of this, but she seemed very very excited about that prospect, I guess.
Yeah. Anyway, guys, this is great. Thanks for the space. I need to bugger off. I have a meeting, so I'll
Thank you
catch
so
up
much
with
for
you later.
coming, Skinny Neville. Very
Nice
appreciate
meeting
it
you,
here.
Stan.
Yeah, thanks. Good to meet you.
Yeah.
If we host
thanks.
these more, you're more than welcome to come and go for your meeting. Hopefully, it's going to be a little more boring than this. Folks, I think at this point, unless some folks on stage want to go for maybe a little bit more, I think at this point we can close this. We started way early. It's been a while. I'm getting winded. This is the third. Eli, is this the third or the fourth stage that we had in the span of less than a week? We started in Thursday, right? Thursday, you came over.
Yeah, I think the third. I missed one of them live, but I did listen to it.
So we're doing this quite a lot, and the information flow is insane, but also like the ability to stand in front of this potential sea change or ocean change and generation, like so many things are happening at once, this multiplied by AI, that it's like also hard to then go fall asleep. But I do wish all of you good night. I think a very good night if tomorrow we get some more positive news, and the more positive news that we get, then the better the night gets, and the better the prospects of
And
all
I
of us
also
are.
want to say really
Sam,
quickly that like I appreciate that you all. I appreciate that you all were very cool, especially you, Alex, and Ada Pi, towards like Iris in particular, specifically with regards to like her gender. I think there was a lot of like negativity around that, and I think that it was heartening to me to see that you all were sort of fighting against that, and I like to see that in the tech community. I'm not involved in the way that you all are. I'm just a coder, but just there's a lot of sort of bigotry, I guess. And I think you all were very. It really just made me happy to see that you all kind of came to her defense in a way. I guess that's my last comment. Thank you.
Thanks, Sam. Thanks for coming up. Thanks for saying this. Folks, Iris is the shit. Like hopefully I'll become closer friends with Iris, because when she came out with like 20 followers, whatever the fuck, and suddenly started spewing like the most insane physics even, and she's a chemist, so she does like other stuff potentially. Folks are starting attacking like for nothing, from no logic basis, from no experimental or science basis. Folks just came straight out of person. I'm like, why the fuck do you care if this moves us forward towards whatever the humanity needs to go? Why do you care? Bring evidence. And so I started getting like real annoyed. And Eli, correct me if I'm wrong, you also like follow some of Iris works. Like the work is impeccable, even though it looks like in a Russian apartment.
Yeah, no, totally, and I mean, in the best, and given that she's working with hazmat in her kitchen, worst traditions of Soviet science.
Yeah, it's awesome, and I do think that the fact that she had like
so
20
I will say, Sam,
is like a point in her favor. This clearly for her was not like, I'll just get a bunch of followers by replicating this. Like I think this is clearly like a passion project.
I didn't know that such like a feedback even exists out there, but I'm not gonna be surprised. I will say this: I'm hoping that Iris at some point will join us in one of these spaces, or either Iris or yeah, hopefully. The communication style, it's hard to parse a little bit sometimes, but also sometimes the English is impeccable. I just will say this, folks, just to add to the potential genius level like understanding of all of this, right? Because like she synthesized first in the kitchen without like the proper materials, etc. And we're gonna see probably some stuff coming out soon. I think she's moving towards some organization lab, like a big lab, not a home lab. But the English level is way above mine, like leagues above mine. And this is a person that lives in like inside Moscow. I lived in Ukraine. I then lived in Israel for 20 years and like spoke English professionally. And now I'm living in the States. I have two American kids, and her English from inside Russia is like leagues above my like epithets and like the way she speaks. In addition to the geniusness of the chemistry and all of this, right? How there's no like it's hard in Russia. I don't know how many of you are bilingual, trilingual. It's hard. So I think we're dealing with like a unique person here. I will go to the floor. And Sam, thank you for noticing this. This is a very important moment where people without like big lab credentials, even though she is connected, could just like start talking online, and this is like will teach many other folks that this is cool. I'm really happy that she's joining this effort.
And
I think on
it's
this,
just
Sam, if you don't mind,
real quick.
or Eli, go ahead.
It's I think the fact that her competence is just so way above the people who are attacking her. They're threatened by it, and they're like trying to assert themselves through bullying, and she's just coming out totally on top.
Yeah, and like calling out the fact that like
So
people were calling her
this point,
autistic,
the last
and
point,
I think that like her response to that was really cool.
Sam,
Yeah, yeah, go ahead.
if you don't mind, Sam, sorry, dude, I really want to finish, and I don't want to interrupt, but I will say like this one thing: the fact that Wikipedia is considering whether or not like a person like this should be included or not in the table of like who replicates, even though she already replicated, is fucking ridiculous. Like the fact that like this is there, and people need to go to like a blog instead of like a well-reputed whatever the fuck source, and do not see the person who replicated this first in fucking home. The fact like it just means that people have like a gut reaction to some of the stuff surrounding her. I think what we're doing is giving like this person like a blue check, whatever, even though she doesn't want to pay. We're just like the followers and the people who are like adding to the science and talking with her. There's a dude Daniel something from Israel, a physicist also that I added to our group, and they had like an incredible conversation. And she replies immediately with like insane stuff, percolation stuff. Eli saw as well. So yeah, we're big Iris fan. Hopefully, we'll get her on one of these spaces. But other than that, I think, folks, I will tell you good night. Like it's been more than 3 hours, 3 and 12. I think I really want to go see what else is out there has been posted while we were talking. Sangyan has been texting me. There's a bunch of stuff. Maybe somebody else moved us forward. I also wish you like go and explore some more of the folks on the list that we've posted. Yeah, I have a whole space tomorrow about something else, about AI. I see some folks in the audience, Zenova and Junaid, what's up, folks? We should see each other very soon, probably 10 a.m. tomorrow. And with that, good night. Oh, one last thing, important. There's so much info here, just insane. Like physicists, we had. Let me do a quick recap. Eli, do you mind to help me do a quick recap before we go? No more like new topics, just like a quick
Really
recap of
super
people.
condensed, sure.
So we had Robert Palgrave, who like many folks recommended him to join, and he was great. We had a new Finnish friend, which Eli, I would love to hear from more. He's great. We had multiple folks on stage talking about the summary of events that happened in less than a week. We had Andrew up here. I think he's still but Andrew was up here in the middle of a replication attempt on US and like talking to scientists. Yeah, I think there was a lot. All of the folk on stage also to bring more knowledge. Eli, without you, I wouldn't like. Thank you, man.